Hi everybody, and welcome back to our continuation of the ruler function from page 61 of the workbook. In the last video, we reviewed the process of taking this definition of our ruler function and plugging in some numbers, and we noticed the different behavior depending on whether we plug in rational or irrational numbers. In this next video, we want to consider the problem of whether or not this function has a limit. Okay, what we noticed in the last video is that the points that we haven't plotted yet all lie below the points that we've already plotted. So rational numbers would wind up in this zone, and irrational numbers would wind up here. And the fact that so many of the numbers that we plug in are close to zero leads us to conjecture that this function actually has a limit. Okay, if we take the limit as x approaches x0 for some number x0 between 0 and 1, despite its strange behavior, this function actually has a limit of 0. And the problem that we're about to do down here, part F, is meant to explore that and convince ourselves that that conjecture is maybe plausible here. Okay, so let's take a look at what part F is asking us to do. They're giving us a specific number, x0 equals 1/4, and they'd like us to find a number delta 3 greater than 0 such that if this statement is true, which is just basically saying that if x minus x0 is less than delta 3, in other words, if x is close to 1/4, then our output values f of x are close to 0, and 1/4 is our measure of closeness here. Okay, so how do we choose this? All right, well, let's start with the statement that we want, okay, that f of x minus 0 is less than 1/4. That creates an epsilon zone that we can actually draw into our picture. Okay, so we'd like to be between 1/4 and negative 1/4. That's where we want all of our output values to lie. And this 1/4 is our starting point. And we'd like to draw a neighborhood around that 1/4 so that all the x values in our neighborhood lie within this epsilon zone that we have here. Okay, what makes this kind of challenging is that there are a lot of points that we can't see on our function that haven't been plotted, okay, again, that either lie in this zone or right along the x-axis. So our strategy in determining this delta 3 is to think about the points that we want to avoid, points that are outside of our epsilon zone. And we can start by circling those. Okay, so for example, these 2 points are way outside of our epsilon zone. X equals 0 and x equals 1, so if we start our list of points to be avoided, they are definitely on that list. Okay, are there any others? Well, yes, there are. Here's one that's outside of the epsilon zone. 1/2, if we try to plug that in, that's certainly not going to give us an output between negative 1/4 and 1/4. And there are a few more points. Okay, here and here, for example, and here, but then we have to remind ourselves something about the condition that we started with here. All right, we insisted that x minus x0 be greater than 0. Okay, that effectively rules out the possibility that x might equal 1/4, okay, because if we plugged in 1/4 for both x and x0, we would get 0, and that violates this condition right here. So the upshot of it is, this really is not a point that we need to avoid. We can cross that off of our list. Okay, that has to do with the fact when we take a limit, we're never worried about what happens right at the point we're considering. Okay, so if we continue this list of points to be avoided, what else was there? There was this point here and this point here. Those are 1/3 and 2/3. And then finally, this point over here, which was 3/4. Okay, and that's a complete list. As long as we avoid all of those points, everything else is going to be okay, including the points that we don't see, the ones that we haven't plotted down here in this range. So the only question remaining then is, how big can delta be so that we don't capture any of those points that we don't want here? All right, and let's illustrate that first by choosing a delta that doesn't work and talk about why it doesn't work. All right, so I'm going to choose delta to be 1/4, which would produce a neighborhood that's that big. Okay, delta goes from 1/4 to 1/2. That's a distance of 1/2. All right, and so just to illustrate that neighborhood, let's draw in a couple of vertical lines. And what we notice is that in that delta neighborhood, between those two vertical blue lines that we drew, there's a point that we don't want right here. Okay, that point is outside of our epsilon zone. Okay, and so this delta neighborhood won't work because it captures that point that we don't want. So we need to make delta smaller, small enough so that it avoids this point that we captured that we don't want. Okay, so let's back up. Okay, erase that neighborhood that we just chose. Okay, maybe redraw some of the stuff that we erased. Okay, and I want to draw a delta neighborhood that avoids that problem point right here. And I claim that if we draw it this small, that's going to work for us. Okay, let's draw in the blue lines and really convince ourselves that if we stay between the blue lines in our delta neighborhood, we're not going to capture any point that we don't want. Okay, so first observation, this unwanted point is now on the line of our delta neighborhood, so it's no longer included in it. And if you look carefully, everything else is, okay, everything that's within those blue lines is successfully within our epsilon zone in this case. Okay, just to give you an example, this point right here is successfully in there. And there are a lot of points that we can't see that are also in that delta neighborhood. So a bunch of points in here, rational numbers that we haven't plotted, and then any irrational numbers are going to be down here. So the upshot of it is this delta that we just drew into our picture should work. And now let's figure out what that delta actually is numerically. Okay, so delta would be the distance from the 1/4 that we started with over to the edge of our neighborhood. Okay, so this horizontal distance that I'm highlighting. And we'll remind ourselves that the point at the right-hand side is 1/3. So that distance is the distance between 1/4 and 1/3. Okay, if we can do that calculation, we have found our delta 3. Okay, and I'll leave it to you to do the arithmetic here. If you subtract those two fractions, you get 1/12, and that's our answer. So we have just demonstrated graphically that if we take x values satisfying this inequality, okay, with delta 3 equal to 1/12, all of our outputs are going to be within 1/4 of 0.